In this course, I don't want to limit you to just one language, because we all code in different languages, and throughout your career, you're most likely going to use multiple languages. Now, this course specifically, I will have to use a language to demonstrate code and write some code. And I'm going to use JavaScript for this because it is similar with a lot of common languages, and it's also the most well-known. However, you can use whatever language you want in this course and follow along. Even the exercises will give you solutions in different languages. So pick whichever one you want. But how are we going to run all these different languages when you're following along? Maybe I'm demonstrating something in JavaScript and you're coding along in Python. Well, we're going to use a couple of neat little online tools. The first one I'm going to show you, and the one we're going to use in this course, is REPL.it. REPL it, as I like to call it. And you can pick any language that you want here to code along. And like I said, I'm going to be using JavaScript for this course. But all you need to do is to sign up with your GitHub account, and you'll have a little IDE that you can run your code with. And you'll see me using this throughout the course. Another one that I really like is glot.io. And it's open source, which I'm a big fan of. And you can see over here that we have a lot of different languages that we can use. Again, if I go to JavaScript, it gives me a nice little area for me to write code and run it. Another option, especially if you're using JavaScript, is to just go to View, Developer, and Developer Tools in Google Chrome. And this allows you in the Console tab to just write JavaScript. So that's another great option. Or if you prefer, you can always use your favorite text editor, write your code, and then run it whichever way you want. Again, keeping in mind that this course is language agnostic. That means it doesn't matter what language you use. What we're learning are foundational computer science principles that you can take anywhere throughout your career. And as you'll see, whether you know JavaScript or not, I'm going to keep the code very general and simple so that it's easy to replicate it into other languages and also give you resources and sources with other languages when we get into more nitty-gritty coding. All right, set up your environment, get ready for some code. I'll see you in the next video. Bye-bye. In my opinion, this section is one of the most important topics for any software developer or engineer. It also happens to be my favorite section of this course. No matter what company you work in, where you live, or even if you're coding 10 years from now, this is a concept that will be around for a long time and something that will truly make you a better developer. Big O is something that I learned about 2 to 3 years into my career as a developer. And it's so important. It has made me a better developer, a better engineer. And it will for you as well. Big companies like Google, Facebook, Alibaba, Amazon, all know this, which is why you won't get by any of their interviews, any of their phone interviews, any of their screening interviews without encountering this topic. So we're going to learn all about this very important topic, and that's why it's at the beginning of the course. All right, did I grab your attention enough? So what are we talking about here? It's called Big O, and the official term is Big O, asymptotic analysis, if you want to sound super smart and impress your friends. You see, any coder, given enough time, can solve a problem. What matters is, though, how well the problem is solved. And this is where Big O can help us. It can tell us how well a problem is solved. We're going to find out about what that means in this section. We're going to talk about Big O, what it is, how we define it, and then we're going to use Big O and its different notation to distinguish bad code from good code from great code. We are going to become comfortable with this topic, that we are going to not be surprised when this comes up in our interviews. But we are also going to build this big foundation that is important to be a great developer. The reason this topic is at the beginning of this course is that you will see this Big O notation come up again and again as we go into topics such as data structures and algorithms. Like I said, this is my favorite section, so get ready because it's going to be a lot of fun. See you in the next video. Bye-bye. There are two main things we talk about when we say this is good code. But before I show you, what do you think good code is? Think about that. What would you tell somebody if you're asking them to write good code? All right, I'll just give you the answer. You see, good code can be described in two things, or 2 points. One is readability. Is your code just generally clean? Can others understand your code? And then we have scalable code. What does that mean? Well, big O notation is what allows us to measure this idea of scalable code that can scale. Something that we're going to get into and you're going to become more familiar with as we go through this section. We're also going to talk about readable code throughout this entire course, but touch upon it a little bit more in the next section. But for now, because this is the big O section, we're focusing on this idea of scalable code. Okay, what does this really mean though? Well, I want you to imagine we have a task where we want to bake a cake. We have a recipe over here, and this recipe we're going to use in our kitchen to bake a cake. And there's a good way of baking a cake and a bad way, right? We give it the instructions, that is the recipe, and hopefully this recipe and instructions work well with our kitchen so that we can bake a cake quickly, and a good cake at that. Well, computers are machines, and these machines need to work in order to produce something for us. And computers work in the same way. We have these instructions that we give it through code, and these instructions that we give to our machines, our computers, give these instructions that provide for us some sort of an output. For example, to turn on the light. We give the computer instruction to say, hey, turn on the light in our room. A coder is someone that gives these instructions. Just like there are many ways to take a cake into a kitchen, or just like there are many ways to bake a cake in the kitchen, with many recipes, ingredients, and instructions, there are many ways to solve a problem through code. There are efficient and inefficient ways to give instructions. So let's go to a coding example. I'm going to use REPL.in. And if you're not familiar with this, make sure you check out the video that I've listed down below here, which explains how you can run your code in this course. I'm going to just log in. And I already have my JavaScript environment set up over here. And I prefer having the dark theme. I think that looks better on your eyes. For you at least, I hope you don't mind the darkness. But how can I demonstrate this idea of code? Let's do something fun here. Using JavaScript, I'm going to say const Nemo. We have an array that contains the string Nemo. And we want to create a function here that is called find Nemo. And this function is going to receive an array. And it's going to be a very simple function. We're going to create a loop that you'll see in most languages. In JavaScript, we can do that easily by saying for, and we'll give let I equals 0. And as long as I is smaller than the array.length, that is the length of our array, and then we're going to increment I every time. Again, this isn't a JavaScript course, so hopefully this is familiar to you. Any sort of loop that you want in your language. And we're just going to simply say that if array I equals Nemo. So if we find Nemo, we're just going to console.log found Nemo. We're very excited we found it. All right, that's it. And if I just simply run the function now, find Nemo, and we'll just give it the array Nemo over here, and make sure that I spell length properly, and we click run here, we have found Nemo on the right. Let me make this a little bit bigger so you can see. So we found Nemo. This is the instruction that we gave the computer. We told it that we have an array, and we have a function, an action that we want to perform called find Nemo that takes an array, which is Nemo. It's going to receive this array. Then it's going to loop over the array. We're going to say that I is going to equal 0. And because I is 0 right now, and the array.length of Nemo is 1, we're going to go through the loop. We're going to check if array index of 0, which is Nemo over here. So this is going to turn into Nemo. And because this is true, we're going to console log found Nemo. Now, why did I just show you this example? Let me just bring this back to the way it was. I showed you this example because this is an instruction that we're giving our computer to find Nemo. You see, we call this the runtime. How long does it take to run a certain problem through a function or a task? How can we measure the big O of something like this, or the efficiency of this code? In the next video, we're going to get a little bit deeper. We're going to try and measure the performance of this code and see what happens when the array gets larger and larger. And we're going to tie things together as to what scalable means and how big O allows us to measure this scalability. See you in the next video. Bye-bye. Welcome back. Let's continue our discussion of what this scalable idea means. You remember that we talked about the kitchen and how, similar to a kitchen, we have to give instructions to our machines to produce a result. And in the previous video, we talked about this function, finding Nemo. Let's measure the performance of this function. Well, JavaScript gives us a nifty little tool that comes built in to the browser, which is where we're running this code. So depending on your language, you might not have this option, but you will have different ways of measuring this. Don't get too hung up on this. We want to use this as an example to measure how long it takes for this function to run. We can do this in JavaScript by saying, let's say time 0 is going to equal performance that comes built in to the browser. And we just say now. And this T0 is going to start this timer before the loop happens. And then when the loop ends, I'm going to have another timer called T1. And this is going to equal performance.now. So we have two timers, one at the beginning, one at the end after the function goes through the loop to find Nemo. And then at the end, we'll just do a fun little console.log, and we'll say that the call to find Nemo took, and we can just do a simple T1 minus T0, and then we'll say milliseconds, because it's going to give us the results in milliseconds. Let's see if this works. I'm going to run this code. And let me add a space in here. And we see that it took 0 milliseconds for this code to run. Let me run that again. 0 seconds, again, 0 seconds, 0 seconds. And if I keep clicking it, I see that, oh, now it takes a little bit longer. And that's because this is really fast, right? Our computers, machines are extremely fast in this day and age. And because we're only looping through this once, well, it takes almost 0 milliseconds. And the display just rounds this down. But what if we had a bigger array? Let's say that we have an array over here that has const everyone, and it has all the characters, or at least a lot of the characters from the movie Finding Nemo, which if you haven't watched it, amazing movie, highly recommend it. Anyway, we see that we have a lot more characters now. So instead of just having a single array, let's have the array everyone in here. And this array now has a lot more items. It has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 10 loops in here that we're going to do. If we run this, we see that the time is still the same, pretty much 0 milliseconds, sometimes a little bit more, and the time changes all the time. But we don't see that much of a difference, do we? I mean, we went from 1 loop to now 10 loops, but it's still super, super fast. And again, that's because our computers in this day and age are quite fast. The difference between 1 loop and 10 loops is not that big. But let's do a little fun trick here. In JavaScript, we can create a large array. Let's just call it large. And we can create a massive array by just saying new array. And we'll give it 100 items. And this 100 items in the array, we can fill it with, let's say, Nemo. And this is just going to create an array that has Nemo 100 times. So instead of everyone, let's do large and hit run. All right, we see here that it's found Nemo 100 times because, well, we just filled it with Nemo. And at the bottom, we see that it took 0.5 milliseconds. That took a lot longer, didn't it? Let's do even bigger. Let's do 1,000. Hit run. It took 7 milliseconds now. What if we do even bigger? What if we had a massive array of 10,000? If we hit run, 46 milliseconds. It's still pretty fast. And then just for fun, one more. If I hit run, you saw that delay and how long that took. That took 343 milliseconds, or 3.4 seconds. Now, what do we just see here? Well, we see that as our input grew, our function, find Nemo, became slower and slower and slower. Our runtime, how long it takes to run a certain problem through a function, increased. But here's the problem here. If you take this code and run it on your computer, well, your time is going to be different than mine. And I'll leave this code at the end of this video so you can play around with it. You're going to get frustrated because every time you run this code is going to be different than my number. It might be a lot faster or a lot slower. You see, this all depends on how powerful the CPU in the computer is and what other programs are running on your computer, what programming languages you're using, and many other factors. So there's all these factors that play here in our runtime. Therefore, if I speak to my friend across the world, let's call him Johnny, and if I tell him, hey Johnny, my code is so amazing, I've created this find Nemo function and it runs in 3 seconds, 3.2 seconds with 100,000 inputs. How good of a coder am I? And then Johnny says, that's really awesome, but you know what? Mine runs a lot faster. It runs in 1.5 seconds. So I win. What do you think? Do you think Johnny wins? Does Johnny have better code than I do? Well, here's the thing. Not necessarily. This doesn't really mean much. Because it matters what type of computer Johnny has, what other factors, as I mentioned before, the code is running in. So how can we determine who wins? Do I win or does Johnny win? Who has better code? And this is very common in the computing world. We code on our laptops, our computers, but that code doesn't necessarily run on those devices. If we have something like a server, we may have that code run somewhere else on a different computer around the world. So how can we make sure that there's a way for us to measure, in terms of efficiency, what is good code and what is bad code? And what is code that can scale? That as the number of arrays or inputs increases, it doesn't constantly slow down more and more. Big O notation is the language we use for talking about how long an algorithm takes to run. We can compare two different algorithms, or in this case functions, using Big O and say which one is better than the other when it comes to scale, regardless of our computer differences. And we can measure Big O like this. I'm going to warn you that this will look really confusing at first, and this is the first time we're seeing this diagram. And don't worry, by the end of this section, this is going to make sense and you're going to be completely fluent in this. So just trust me in this. Keep following these videos. I know I'm kind of circling around the topic and not being direct as to what it means, but I promise you, by the end of this is all going to make sense and you're going to be a Big O ninja. When we talk about Big O and scalability of code, we simply mean when we grow bigger and bigger with our input, how much does the algorithm or function slow down? If the list of characters, let's say elements here, so that is Nemo, so characters in Finding Nemo in our array, as that increases, how many more operations do we have to do? That's all it is. This is what we call algorithmic efficiency. Big O allows us to explain this concept. Remember how in our function, we initially had an array of just one, which was Nemo. So that is the number of elements, number of inputs in a function. It was right here. But then as we increased that array to have more characters, and then we created that massive array of 100,000. So as that increases, you saw that the number of operations or the number of things we do in the loop increased over and over. And different functions have different Big O complexities. That is, these number of operations can increase really, really fast, like this one, which is not good. You can see here that it's horrible. And things that are quite good, actually, and don't increase as much. And we're going to look at examples of different ones and how to actually measure this and what this entire notation means. But to end this video, so we can dive deeper into the topic, just remember this point. When we talk about Big O and scalability of code, we simply mean when we grow bigger and bigger with our input, how much does the algorithm slow down? The less it slows down or the slower it slows down, the better it is. So instead of using performance.now and using time to measure the efficiency of our function, we can just calculate how many operations a computer has to perform, because each operation takes time on a computer. So Big O allows us and concerns us with how many steps it takes in a function. All right, let's dig in deeper and deeper into this topic. I'll see you in the next video. Bye-bye. What would you say if I asked you, what is the Big O of the function Finding Nemo? Well, to make this a little bit cleaner, let's just remove performance.now because we've learned that it's not very, very important. And we can remove the console log as well. And looking at this and this loop, what would you say the Big O is? In this video, we're going to learn about our very first big O notation. As we said, a runtime is simply how long something takes to run. How does this function and its runtime grow as our input increases? As our input goes from just a single item in an array, Nemo, to 10 items in an array, to 100,000. How does the efficiency of this function increase? If we look at this graph and we say we have 4 items in the array, well, the number of operations is going to be 4, right? Because we're going to loop through each item and say, is this Nemo? Is this Nemo? Is this Nemo? Is this Nemo? 4 times. No matter what, we're looping 4 times, at least with the way that we have this code set up. If we have 5 items in the array, it's going to be 5 operations, 5 loops. 6 is the same. 6 items is 6 operations. 7 is 7 operations. And 8 is 8 operations. Do we see a little bit of a pattern here? Well, we can draw a line through it. This is linear, right? As our number of inputs increase, the number of operations increase as well. And here, ladies and gentlemen, we've learned our very first big O notation. We say that the finding Nemo function has a big O notation of O n. That's a little bit strange. This is just a notation that you have to get used to. But we say big O of n, or what we call linear time. It takes linear time to find Nemo. Now, where does this n come from? This n can be anything, really. I could put x, I could put fish in here if I want. It's just an arbitrary letter. And we usually give n when it comes to big O. This is just a standard that you'll see across the board. N simply means the big O depends on the number of inputs, the number of fish. So if we just had the Nemo array, this would just be 1. If we had the everyone array, this would be 10. And if we had the large array, it'll be 100,000. But as the inputs increase, you see that the number of operations increase linearly with it. O(n) is probably the most common big O notation you'll find. If we go back to the graph, you can see that O(n) is right here in the yellow region that says fair. As the number of elements increase, you see that it's just a straight line. The number of operations increases by the same amount. Because keep this in mind, big O doesn't measure things in seconds. Instead, we're focusing on how quickly our runtime grows. We simply do this by using the size of the input, which we call n, or anything else that we want really, and compare it to the number of operations that increase. That's what scalability means. As things grow larger and larger, does it scale? So the find Nemo function is O of n, linear time. Another way to think about it is this. If we had a compression algorithm, let's say this function is this little compression, and the input is this little box. What's the big O notation of this function? Well, if we had one element, it will just compress one item. If we had multiple elements, again, we still have to run each box through the compression algorithm to compress the box. If we look at the function for the compress boxes, well, we're using the ES5 and ES6 syntax here, but we're essentially looping through each box. And in our case, we're just console logging it. But you can see here that all of these, all we're doing as the input increases, the number of boxes increases, the number of operations increase. And that is O(n), linear time. Congratulations, you just learned your first big O notation. And this is probably the most common. But there's a few others. So what other big O notations do we have other than linear time? For that, you're going to have to keep watching. I'll see you in the next video. Bye-bye. Welcome back. We just learned our first notation, O of n, or linear time. And we see here that we have a few others remaining. So let's talk about the next one. Another very common big O notation that you're going to see. What happens if we have a function like this? A function that says compressed first box that receives an array of boxes. And this function simply has console.log boxes 0. So that is, it's logging out just the first item in the box. what would you say the big O of this function is? How many steps or operations does this function take if the boxes increase from 0 to maybe 10 to maybe 100 to 100,000? What would happen here? Ready for the answer? Well, this is what we call constant time. It's an O of 1. That is, no matter how many times the boxes increase here, or however many boxes we have, we're always just grabbing the first item in the array. If we look at this with an example, if we had an array of boxes here, and we run it through the function that just takes the first item in the array, well, the number of operations is 1. No matter how big the number of boxes are, we're only doing one thing. So it's a constant time. If we look at this on a graph, if we have one element or one box, we do one operation. If we have 3, again, we still do just one because we're just grabbing the first item in the array. If we have, let's say, 5, same thing. 7, same thing. And what about 9? Again, same number of operation. And this is, I don't know if you can see the line, but this is just constant time. It's not linear time like it was, where it increases and increases with the number of operations. The number of operations just stays flat. But I have a question here. What if we do something different? What if we do something like this? What if we have a function that says function grab or log first 2 boxes? And this takes an array of boxes and it's going to console.log the first item in the array, and it's going to console.log also the second item in the array. How do we measure the big O of this function? Well, let me just comment this out for a second because we don't need this right now. And just create an array called boxes. And this boxes has, let's just say 0, 1, 2, 3, 4, and 5. So 5 items, or 6 in this case, because we include 0. And if we run this function, log first 2 boxes, and we give it the boxes array, and we click run here, we have 0 and 1. So we've logged this one and then this one. What's the number of operations here? Well, we have O of 1, that is one operation here, and then we have over here O of 1 again. Each time, this function runs 2 operations. So this function in total is actually running O of 2 operations every time. So no matter how big the boxes get, the number of operations here is going to be 2. If we look at this on a graph, instead of having O of 1 like we had before, we have O of 2. And then if we had 3 operations, it'll just be O of 3. But overall, it's still a flat line. And this is something we're going to get into later on. But when it comes to constant time, we don't care about the nitty-gritty O of 1, O of 2, O of 3, O of even 100. We round this down to just simply saying O of 1. That is, we have constant time. It's a flat line. In terms of scalability, it doesn't matter how big our inputs are. We're always going to do the constant amount of time on a function. And if we look at this on a graph, we see that O of 1 over here is the dark green area. It's excellent. We love O of 1 because it's very scalable, right? It doesn't matter how many elements we have, it's always going to run the same. Predictability when it comes to computing is very, very nice. And O of 1 is definitely excellent. Okay, so we've learned about linear time, O of n, and then constant time, O of 1. Let's do a bit of a fun exercise to really solidify our knowledge here. Welcome back. How much did you hate me after doing this challenge? Now, this was specifically supposed to be hard and difficult and frustrating, and most likely you're not going to get right the first time around. This was done on purpose to illustrate a point. What we're actually doing here, well, you won't be asked to do in an interview. But I wanted to show you how to think about things because later on, I'll show you how it's actually a lot simpler than thinking about each individual step in a function to calculate things. There's not much math involved, and this is as mathy as we're going to get in this course. But again, I just want to show you the nitty-gritty details so that you can think about it and have a nice foundation so that moving forward, we can simplify things a lot better. Now, let's look at this function. It's the fun challenge function that takes some sort of an input. The very first thing is within this function, when we run the fun challenge, let's just say we'll have fun challenge and we run this function and the input doesn't really matter. It could be an array, it could be an object. For now, let's just keep things simple, say it's an array of 5. Now, when we run this function, the first thing we're going to do is an assignment. We're going to assign variable a as 10. Now, based on convention, and this is why you won't encounter this in an interview because a lot of people interpret this differently. Some people say that assignment you shouldn't count towards big O, and some people say that you should. In our case, just to simplify things, let's count every single step and what the function is doing. Let a equals 10 is just O of 1 because this is only running once when we run fun challenge. That's it. It doesn't matter how big the input is. This just runs once. And then 50 plus 3, we're reassigning a. This, once again, is O of 1. And then we get into a loop. We know that with the loop, it looks like we're looking at the length of the input and looping over depending on whatever the input is. In our case, this is going to be an O of n. Let's add that comment over here. And this n is the input. Remember that I can change this to input, I can change this to x, it doesn't really matter. It just reflects how big the input is. That's how long this for loop is going to take. And we know this by now that loops are linear time. And then within here, another function. We don't know what this function is, but it's calling to another function outside of the fun challenge function. This is also being called how many times? Well, it depends on how big our input is. So once again, it's O of n. What about this? Let variable stranger equal to true. Again, another random assignment here, but this runs as many times as this loop happens. If input was 5, this will run 5 times. So again, this will be O of n. And then over here we have a plus plus, which in JavaScript simply means a plus 1. So we're just incrementing the whatever the number a is at this time. So 53 will become 54. And then as we loop through it, it'll keep increasing by 1. 54, 55, 56. This, once again, runs O of n times. It depends how many times it runs by the input because, again, we're looping through it. And then finally, another thing that some people don't count, but just to keep it consistent, every single step that we do, return A. This runs just once. Every time fun challenge gets run, the return statement only runs once. All right, so we have all these big O notation. And now we're starting to think about how a function runs and how efficient a function is. If we actually calculate all of these, if we total all these up, we see that we have 1, 2, 3. So we have 3 steps plus O of n, O of n, O of n, O of n. So that means we have n plus n plus n. So that means we are running the calculation n plus n plus n plus n, which turns out to be 4n. So 3 plus 4n is our big O notation. There it is. Like I said before, when it comes to big O, don't get too hung up on, did I get this right? Because in an interview, you're not going to need to know this. But you are able to now think about how a function runs more deeply than just simply writing the code. As we progress through the videos, you're going to find out that this actually, at the end of the day, gets simplified to just O of n. And we're going to go through that and why that is. Now that we have a better understanding of how to calculate big O, let's look at another exercise that should be a little bit easier than the first one that we did. What would you say that the big O of this is? Well, if we go one by one, we see here that we have O of 1, again, O of 1. And you know what? If I keep typing this is going to get tiresome, so I'm just going to copy and paste. So O of 1 here, we're just assigning variables. And then we also see here that we have a for loop that is running based on the input. We don't know what that input is, but we can just assume that we're looping based on however long this input is, in which case we're running each one of these O of n times, or whatever long the input is. So again, these are going to be run O of n and O of n times. And if we go down here, again, same thing. We don't know what the input is, but these are being run O of n times. And then finally, this last line is just run once. So it'll be O of 1. So looking at this function, another fun challenge function, we see that our O of n, our big O, is 1, 2, 3, 4. So we have 4. Plus, because we're just adding up the steps here, we have O of n that's happening 1, 2, 3, 4, 5. So 5n. So the big O here is we have 4 constant times, and then 5 things that we're doing n times, or however long the input is. All right, that wasn't so bad, was it, compared to the first time around? I think you're starting to get the hang of this. So let's dive into the next video. Let's start to figure out how we can simplify things for us so that we're not doing this mathematical step-by-step count. I'll see you in the next video. Bye-bye. Welcome back. Now, in the previous exercise and the exercise we just did, we see that we had to do a bit of calculation. It was kind of annoying where we had to add things up, then have this, plus 5n plus 4. In interviews, you're never going to do this. And you're asking yourself, Andre, why did you just teach me this? And you're right. But now you at least understand how big O gets calculated. But most of the time, when you go into interviews, there's these set of rules that you're going to follow, where you don't need to do this, and you can just take a look at this function and immediately say what type of big O it is. For example, this function actually just turns into O of n. This function, again, turns into just O of n. And this is a nifty little trick. When we talk about big O, in interviews, most of the time, you're only going to give one of these answers. You're most likely never going to actually calculate precisely O of 3n or O of 3n plus 2 plus 1. So how was I able to simplify our exercises and just say that they're O(n)? And luckily for you, there are just several rules that we can follow when it comes to big O. And there's only 4 of them. By following these 4 rules, instead of doing those small little calculations that we've been doing up until this moment, you can just simplify your life so that big O becomes really, really easy to calculate. Let's tackle the first one. That is rule number 1, worst case. Let's talk about that in the next video. Welcome back. Let's talk about the very first rule when it comes to big O. That is worst case. When calculating big O, we always think about the worst case. What do I mean by that? Well, if we go back to Finding Nemo example. In the Find Nemo function, you may have been screaming at me while I was going through the function, saying that, Andre, this is not efficient. What are you doing? Because if you look at this function, we're looping through the entire array to find Nemo. Remember how we had the everyone array with about 10 different characters from Finding Nemo? Well, Nemo was only the 1, 2, 3, 4th member on this array. And when we run this function, we found Nemo. But the funny thing is, this function ran 10 times, not 4 times. If I do a console log here, and I say running, and let's click this, we see that this function ran 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I mean, we already found Nemo. All these runs are pretty wasteful. So we can make this function a little bit more efficient. In JavaScript, we can just have something called break. And again, different languages have different ways of exiting out of a loop if a condition is met. In our case, if we find Nemo, just break out of this loop. If I do this and click run, look at that. Once we found Nemo, we're done. We're not going to loop through the rest of the items. Congratulations, we just made our code a little bit more efficient. That's a good thing, right? Well, when it comes to big O, Although this is important, and when you write good code, this is something that we want to do. In the big scheme of things, Big O only cares about the worst case. What is the worst case here? Well, the worst case is that Nemo, instead of being the fourth item, is at the very end. So even if we have this break statement, we're still going to run this 10 times because Nemo at the end. Best case is if Nemo's at the very beginning and we only have to loop through it once. But worst case, we're still going to have to go through 10 loops. Still Big O of n. So this is our very first rule. The very first rule is we always care about what is the worst case scenario, because when we talk about scalability, we can't just assume things are going well. Even though the find Nemo function might be O of 1 if Nemo is the very first item in the array, it doesn't matter. In the grand scheme of things, because we can't be certain of what the input is going to be, we're going to assume that O of Big O is O of n, linear time. Again, if we're finding a yellow box and the yellow box is at the very end, we have to iterate through all the boxes. If the yellow box is at the very beginning, you see that we don't have to iterate through these boxes. But Big O doesn't really care. Even though this function, yes, is indeed more efficient, at the end of the day, when we talk about Big O, we're talking about worst case. All right, I hope you got that point through. I feel like I've beaten it to a pulp, so you should be comfortable with it by now. Let's talk about the next rule in the next video. Welcome back. Let's look at rule number 2. That is, remove constants. Let's see what I mean. I've written here the most ridiculous function ever. The function is print first item, then first half, then say hi 100 times. Probably not the best named function ever, but as the name describes, all we're doing is we're going to console log the first item in the array, and then we're going to print the first half of the items. So I'm finding the middle index of the items. So I'm saying items.length divided by 2, and I use math.floor here in JavaScript as a way for us to make sure that we get a whole number, and we're going to say variable index is 0. I'm using a while loop here instead of a for loop, and I'm saying as long as middle index is greater than 0, I want you to console log the items. So that means console log the first half of the items. So if we had 10 items, I'm going to console log the first 5 items. And then I'm going to do another for loop and say I'm console logging hi 100 times. Pretty useless, I would say. Not a very useful function. What is the Big O of this function? Well, looking over here, it's going to be Big O of 1 over here. So we have 1 for just logging the first items. Then we have half of whatever the items is. So in our case is n divided by 2. Because even though we have a for loop or a while loop, we're only logging half the items every time. So we can just do n divided by 2. And then finally, we're doing a for loop. But again, this is a bit of a trick. We're not looping over the items array. We just have 100. No matter how big the items array is, this is going to be always 100. So I just say plus 100. It's another step. Because again, we're just adding each of the steps that we see here. So this is our Big O for this function. But rule number 2 states we want to drop the constants. We simply are saying that we don't really care that this Big O is actually n divided by 2 plus 101. Remember, in an interview, we only care about the things that we saw on the chart. Nothing specific like this. So this turns into 1. And this, even though it's divided by half, in the grand scheme of things, we only care about when it scales, when the inputs are getting larger and larger. So as n gets bigger and bigger, we don't care about adding an extra 100, because if n is 1,000,000, adding an extra 100 on there, another 100 steps, doesn't really matter. And same with dividing by 2. As n gets larger and larger, dividing by 2 has a decreasingly significant effect. So we drop the constants like this. So this becomes O of n plus 1. Okay, and because 1, if n was a million, is very insignificant, we can just drop this as well. This function just becomes O of n. What if we had another function that had, let's say, O of a plus 50? Or a of 50 with a ton of zeros. It doesn't really matter. We drop the constants. It's going to be O of a. What about this other situation? What if we have this function here, compress boxes twice, where this function actually has 2 for loops, where it does the same thing, but it's 2 for loops. So we have O of n in this for loop, and then O of n in this for loop. And because these are 2 separate steps, well, we add them together. So it becomes O of n plus O of n equals O of 2n. But again, in an interview, this doesn't really matter because we drop the constants. And if we drop the constants, what does this function equate to? Well, it's just O of n. To prove that I'm not lying to you, if we look at this function on our graph, we see that the elements, as the elements increase, we have 2 operations because we have 2 for loops. If we have 2 elements, in that case, we do 4 operations. If we have 3, then we do 1, 2, 3, 4, 5, 6. And you see how it increases. But at the end of the day, even though the line is steeper, we have a lot more operations to do. The way the line increases is still linear. And that's the key here. With big O, we don't really care about how steep the line is. We care about how the line moves as our inputs increase. Makes our lives a whole lot simpler, doesn't it? So remember, drop the constants. You're never going to really see numbers in big O notation. Most likely the notations that we've seen in the past before on our graph. Usually these, and the only time you see numbers is when you have O of 1, O of n squared, or O of 2 to the power of n. Which we'll get to later, don't worry. I'll see you in the next video. Bye-bye. Welcome back. Let's talk about rule number 3. That is, different terms for inputs. And this is one of the trickiest parts of an interview that a lot of people make mistakes on. But once you understand it, it becomes really easy to spot. So let's look at an example. I have the exact same function we saw in the last video. Compress boxes twice. We have the boxes array, and we just have 2 loops here. I'm using the for each syntax in JavaScript, but we're just looping twice over the same array. And as I said before, the big O of this is going to be 2n. But because we drop the constants, it becomes O of n. But the third rule states that different terms for inputs. And what that means is, well, first of all, let me ask you a question. What if here I have boxes as the first parameter, and then we have boxes 2 as the second parameter? And maybe this second for loop actually loops over the second boxes. What happens here? What is the big O? And during an interview, a lot of people trip up and say that this is, well, still O of n. It's going to be O, 2n, drop the constants, O of n. Now, is this right? No, because the third rule states that different terms for inputs. And remember, boxes, the first one, and then the second one are 2 different inputs. One could be 100 items long. Another one can be just 1 item. So this first for loop is going to depend on how big the first item or first input is. And then the second for loop depends on how big this one is. And n is just an arbitrary letter that we decided on. In this case, the big O of this function would be something like A for the first for loop, which is the first input, plus B. The big O of this function is actually A plus B, or n plus m, or boxes 1 plus boxes 2. So keep that in mind. Just because you see 2 for loops, one after another, doesn't mean that they're looping over the same items. Now, you might be asking yourself, Andre, what happens if these loops are nested? So far, we've only worked with loops that are one after another. What if this loop was inside of this loop? Well, let's get into the next video and talk about another common pattern we see with big O. that is nested loops. One common interview question that you might get is something along the lines of log all pairs of array. Now, what does that actually mean? Well, if we had an array, we'll just say boxes, and this array is just contains boxes numbered 1 through 5. Now, this array, if I want to log all pairs, it means that I want to log 1, 2, then 1, 3, then 1, 4, then 1, 5, then 2, 1, then 2, 2, 2, 3, 2, 4, 2, 5, so on and so forth. How will we go about doing that? And if you want, you can pause the video and try to attempt this problem yourself. Now, in this case, what we want to do is, well, we create a function and we'll say log all pairs of array that receives an array. Let's just say array, so we're descriptive here. And in here, we will do a for loop. So for let I equals 0. And we've done this before, so if I is less than the array.length, and we'll increment I. Now in here, we want to loop, so now in the first iteration of the for loop, we'll grab 1, but then we want to loop through the boxes again and log 1, 1, 1, 2, 1, 3, 1, 4, 1, 5. So we have another for loop, and this time we'll say let j equals 0 if we want to loop from the beginning, or I could even say 1 if we want to start off with 1, 2, because we're starting off at index of 1 right here. For now, we can just leave it at 0. And we'll say that as long as j is less than array.length, and we'll increment jj. And now finally in here, I can just say console.log I and j. Let's run this function and see what happens. Oh, I have to actually call this function. So let's do that. Log all pairs of array, and I'll give it the boxes array. Oh, and we want to make sure here that we're logging out the actual items and not the index of the array. So we'll just say array I here and the array j here. And just so you don't get confused with the numbers, maybe we'll change these into letters so that it's more obvious what we're doing. C, D, that's not D, that's D, and we'll say E. So if I click run here, we see that we're logging all pairs. AA, AB, AC, AD, keeps going until EE. You can see the log over here. What is the big O of this? And this is something that you're going to see a lot of in interviews. And a good rule of thumb is if you see nested loops, that means instead of having 2 for loops, one after another, where we use addition, when you see loops that are nested, we use multiplication. So this becomes O of n times O of n, which when we multiply them becomes O of n squared. O to the n to the power of 2. And that's a good rule of thumb. And if we go back to our graph, this function that we just created, and I'm using the ES5 syntax here instead of the for loops we did, this O of n squared is what we call quadratic time. That means every time the number of elements increase, so let's say we have 2 elements, we have 4 operations that we do. If we have 3 elements, this actually increases quadratically. That means instead of 4 operations, we now have 1, 2, 3, 4, 5, 6, 7, 8, 9. Because we have 3 elements to the power of 2. And you see here how the line is now bent and it increases, well, quite fast. If we go back to our big O notation or big O graph, we see that O of n squared, well, it's horrible, as in it's pretty slow. As the number of elements increases, the number of operations increases significantly. And a lot of interview questions are questions that ask you to solve a problem that initially is O of n squared and make it faster by perhaps making it into something that is a bit low over here. That is bad, fair, good, excellent, but definitely not horrible. if we go back to our rule number 3 that we were discussing, different terms for inputs. Well, going back to that example we had in the previous video, remember this? Well, we said O of A plus B because we had 2 different arrays or inputs. Now, if these loops were actually nested and they're not one after another, the big O would have been O of A times B. And that is rule number 3, making sure to know that we have different arrays. That means different notation for each array because we don't know the lengths. And an easy rule of thumb is any step that happens in the same indentation, so one after another, you add. And anything that happens with indentation that is nested, you multiply. So again, different inputs should have different variables. Let's move on to the last rule in the next video. Oh, we can feel the end, almost. We're in rule number 4, the final rule in our rulebook. Drop non-dominants, or drop non-dominant terms. What do we mean? Let's have a look. Let's say we have a function, again, with a really long name that says print all numbers, then all pair sums. Maybe not the best name for a function. We can probably work on the readability here, but let's see what this function does. Well, this function takes numbers, and these numbers variable, we're going to loop over them with a for each loop. So again, just looping over and logging out the numbers. And then we have another step, which should remind you that's probably an addition that we're doing. We're adding another step. And in here, we're summing the pair sums. That is, we're adding each number one after another. Let's show you with a little bit of a demo here. If, let's say, we create, actually, we'll just print numbers. And in here, for the numbers, let's just give it an array of 1, 2, 3, 4, 5. If I click run here, we see that these are the numbers 1, 2, 3, 4, 5, because this is the step. We're just logging it out, nothing too difficult. And these are their sums. All we're doing is adding 1 with 1, then 1 with 2, which equals 3, 1 with 3, which equals 4, 1 with 4, which equals 5, and 1 and 5, which equals 6. And then we move on to the next loop, which is 2 and 1, which equals 3, 2 and 2, which equals 4, and it keeps going on and on and on. So we see the loops that we've done here. And problems like this is something we're going to do later on in the course. Right now, we're just worried about big O. What do you think the big O notation here is? Well, once again, if we do O of the first part is the for loop. So we can say that there's O of n. And then the second part, which again is another step. So we're going to say add plus. This one has 2 for loops nested. So that means O to the power of 2. All right, so that's our big O notation. But rule number 4 states that we want to drop the non-dominant terms. That means we care about the most important term. In this case, we actually drop the n and just have n to the power of 2 because as the input increases, the size of n to the power of 2 is way more important than the n. So we always just keep the dominant term. Let me give you another example. What if we had a function that had a big O of, let's say, x to the power of 2, and then we'll say that it has 3x plus 1000, and maybe we'll say plus x divided by 2. All right, that's really, really confusing. That's math. We're not gonna want to deal with that too much. How do we simplify this based on the drop non-dominant terms? The 4th rule states that, again, we worry about the most important dominant term because x to the power of 2 is the most significant. That is, if x is 5, 5 to the power of 2 is 25. 5 times 3 is 15. This is 100. And 5 divided by 2 is 2.5. In this case, the dominant term is 100. But remember, with big O, we're worried about scale, and as things grow larger and larger and larger. So when this becomes 5,000, well, 5,000 to the power of 2, or 500 to the power of 2, that's 250,000 if I did the math right. 3 times 500 is only 1,500. 100 is now insignificant, and 500 divided by 2 is 250. You see how this has grown significantly more? Again, because we're only worried about scale here, we drop everything else and we can just ignore it completely, and this becomes x to the power of 2. How nice is that? Just makes things so much simpler. So there you have it. We have now a way to simplify everything. If we go back to our past examples, remember this one? Remember this one? It now makes sense why we've just said big O of n, because we don't care about the insignificant items, only the most important ones. And same with this one. By the way, a fun little note here. If we had another loop inside of these two loops, well, this would become O to the power of x cubed, or n cubed, doesn't really matter what we have, but it's going to be to the power of 3 because we have 3 nested layers. And you can keep going. You can have to the power of 4, to the power of 5. But here's the thing. If you have 3 nested loops, 99.99% of the time, that's usually a bad idea. It scales really, really badly, and most likely you're doing something wrong. And there you have it. We've gone over the 4 rules. And with this in mind, we're going to take a look at the cheat sheet that I've prepared for you. So from now on, instead of having to calculate everything and really look at every single detail of a function, you can right away figure out what the big O is, or what the time complexity of a function is. Now, I've created for you a nice big O cheat sheet. Although we've taken a lot of time to go through everything, at the end of the day, when it comes to preparing for an interview, this is pretty much all you need to know. And you can use this to review some of the topics we've covered, as well as what we're going to cover for future sections. We see here that the big O's, they're mainly these ones over here. Now, we haven't gone through everything. We've gone through constant time, but we haven't gone through something like O log n, or O(n) log n, or O to the 2 to the power of n, or even this one with the exclamation mark. I wonder what that is. Well, we're going to get into that. But the reason I haven't talked about them yet is because they're going to come up when we talk about data structures and algorithms. These commented out big O notations are very specific for certain algorithms and data structures to optimize code. So we're going to get into that when we talk about these topics because they'll make more sense to you. Such as O log n is used a lot when it comes to searching algorithms. Or O(n) log n is used a lot when it comes to sorting algorithms. And something like O2 to the power of n comes into play when we talk about recursive algorithms. So again, don't get overwhelmed. We've talked about these 3 major ones, and we're going to come back to the rest throughout the course. Now, when it comes to big O's, I want you to keep in mind 2 things. When you're iterating through half a collection, it's still O to the power of, or O to the n. Remember, O(n) divided by 2, it's still, at the end of the day, O(n). Remember our rule book. And again, another trick that often comes up in interviews is that 2 separate collections should be A plus B, or if they're nested, A times B. So 2 separate inputs should have 2 separate variables in big O notation. And just to keep in mind what causes time in a function, because that's what we're measuring right now, well, operations, comparisons, looping, we know that takes a while, and things like outside function calls when you have a function inside of a function. And then finally, we talked about our rule book. Always, big O measures the worst case. We want to remove constants. We want to have different inputs that have different variables. So O, A plus B, A and B are arrays. If they're nested, are A times B. Again, something that we've mentioned up here. The easy way to remember this is addition for steps in order and multiplication for nested steps. And then finally, rule 4 is to drop non-dominant terms. Pretty simple, right? I'm going to bring this big O cheat sheet back when we start talking and filling our gaps with the rest of the big O notation. But for now, let's get into the next lesson. Welcome back. You may have noticed something while talking about big O. Scalable means we worry about large inputs. What does the end of the graph look like? So if our function is only worried about really small inputs, or we know that our inputs are only going to be, let's say, an array of 5 items, big O won't matter as much, does it? Because Over here, if the elements are small, all these lines are kind of bunched up together. They're all the same. But is that real life? No, because as humans, we tend to think in here and now. We tend to think that, our website's only going to have 100 users. That's it. But what if that user base grows? What if our inputs grow? We never know. When we write code, we want to write code that can scale so that we don't have to constantly go back and fix things, or when things get out of hand, the code breaks. And that's why Big O is so important. To write scalable code means thinking outside of just this small little section over here. It means thinking long term, thinking big about your code and what could happen in the future. Now, you're thinking to yourself right now, hey, Andre, I feel like I just learned a whole bunch of theory and no practical information. Andre, I want to know exactly how I can use this in my day-to-day life as a coder. I'm kind of getting bored here. Well, with this newfound knowledge, you're going to look at code differently now, right? Let's have a look. You see, now, when we look at methods that we get in a language, such as methods in an array, when it comes to JavaScript, we have things like push, pop, shift, unshift. You see, all these methods, which are functions, have a cost associated with them, a big O cost. For example, when it comes to arrays, when we search for an item, or when we access the first item in an array, for example, it's O of 1. But when we use something like unshift, well, it actually turns out to be O of n. And why that is, we're going to get into when we talk about the data structure array in the data structure section. But you're going to start to see for the rest of this course how we use Big O to measure why one data structure might be better than others. Why should we use an array instead of, let's say, an object? Maybe object has better functions that we need for our data. This graph that we've talked about up until now is actually part of bigocheatsheet.com. And if we scroll down here, you'll see that each data structure, that is an array, and in this case, objects on this table is a hash table, again, something that we're going to cover in the data structure section, but we see that we have different Big O notation for different data structure. And some data structures have really good search Big O, some have insertion, some have deletion, and you can see here that there's different pros and cons to each of these data structures. As you'll find out in this course, data structures are simply ways to store data, and algorithms are simply functions or ways to use data structures to write our programs. Remember, our instructions for machines, for our computers. And great programmers have this knowledge where they pick the right data structure, the right algorithms to write good programs. Remember our two rules of good code, readable and scalable. And what we've learned is the foundation for us to make a decision of which data structure is going to be best when we get into the data structure section, because we're going to know, arrays allows us to access at O and 1, constant time. But when it comes to searching through an array, it's going to give us linear time versus perhaps maybe an object. So behind the scenes, even though this section may be a little bit theoretical and boring, what we've just learned is going to lay the foundation for the rest of the course for us to be able to write good code. For the rest of the sections, we're going to use Big O to see what is a good solution to a problem and what is a bad solution to a problem. And most interviews have this core concept. What's the right data structure? What's the right algorithm to write good programs? Google hires engineers and developers that know this because they have a lot of scale that they have to think about, a lot of inputs. And people that know how to handle these programs are the ones that are going to be able to build great programs. I'll see you in the next one. Bye-bye. Let's quickly talk about a Big O notation that you're most likely not going to encounter. And if you're writing any code that has this Big O notation, you're definitely doing something wrong. It's the most expensive one. It's the steepest of them all. And this is called factorial time, or as I'd like to call it, the oh no. We're not even going to do a demonstration on this because you're just not going to encounter it. I just want to show you that it exists. With O and factorial, and this is a mathematical notation with an exclamation mark. You can search for it and see how it works underneath the hood. But with this, it means that we're adding a nested loop for every input that we have. Yeah, that sounds pretty terrible, doesn't it? Again, just to keep in mind and to get this out of the way, O and factorial, Probably never going to see it, but it's there, and it kind of looks cool. So we can cross another one off our cheat sheet. O(n) factorial, you're adding a loop for every element that you're iterating over. Yeah, it's an expensive one. I'm not going to see it much. So I'll see you in the next video. Bye-bye. What is good code? By this point, you should be able to talk a little bit, especially about scalable, right? I mean, readable, we're going to talk about in the next section, but scalable, we understood was big O, right? Well, here's the thing. Don't hate me, but I may have slightly lied or simplified things, but not that much, so don't worry. We're going to build on that. When I say scalable, there's actually two things that we want to consider as engineers. One is speed. That's what we've been talking about up until now. How fast is our runtime on the code? How much time does it take for a function to run? How many operations does it cost? Well, there's another aspect when it comes to machines. Two valuable resources. One is the time and speed of our code, and the other one is memory. You see, computers have limited memory. Back in the day when computers were just being born, memory was very, very expensive. We only had a little bit of it. And as time has gone on, we have more and more memory, but it's not infinite. Our computers run based on speed, which is usually dictated by the CPU, and memory, based on how much memory, such as RAM and random access memory, the computer has. And those are two valuable resources. So how can we talk about memory? We've talked about speed. What about memory? And the good news is that memory is fairly simple, not as complicated as speed, and it won't take as long to learn as much as we have about speed. Right now, which code is best can be answered with the 3 pillars of code, something that I want you to take with you for the rest of your career, and something that's going to grow you as an engineer, because from now on, when you write code, you're going to have these 3 things in mind. One is you're going to write readable, clean code that others can read, that is maintainable. The other one is speed. The type of code that we call time complexity has a big O time complexity that is efficient. It scales well. But we're going to talk quickly about this third pillar, and that is memory. What's the memory usage of code? If it uses a lot of memory, that's not good. We might have limited memory on our machine. With this one, we use big O once again to talk about space complexity. The same notation, but different topic. One is space, the other one is time. One is speed, the other one is memory. I'm going to give you a quick little preview. Most programming code solution, there's usually a trade-off between speed and memory. You want things to go faster? Well, then you might have to sacrifice more memory. You want less memory? Well, then you might have to sacrifice with increased speed. Let's get into the nitty-gritty of how we measure space complexity. When a program executes, it has 2 ways to remember things: the heap and the stack. The heap is usually where we store variables that we assign values to. And the stack is usually where we keep track of our function calls. Sometimes we want to optimize for using less memory instead of using less time. Talking about memory or space complexity is very similar to talking about the time cost. We simply look at the total size relative to the size of the input and see how many new variables or new memory we're allocating. How much memory is being used. So let's look at an example. Up to this point, we've talked about time complexity and how if we want to compress, let's say some boxes, we just talked about how fast and how many operations this would take. But in real life, there's this other factor of memory. And we have this pink little box of how much this function can take, how much input it's able to take. For example, if we had a ton of boxes that we have to create to run this function, well, it has limited capacity and it might overflow. By the way, things like Stack Overflow is something we're going to be talking about and how it's an issue when it comes to memory. Something we'll cover when we get into recursion. What causes this space complexity? Well, luckily for you, I added this to our cheat sheet. What causes space complexity? Well, adding variables, adding data structures like arrays, objects, hash tables, again, things we'll talk about, function calls, and allocations. We don't need this period. But let's actually code something and show you an example. In the next video, we'll go through some space complexity exercises and figure out how we can give big O notation to the subject. Welcome back. Let's talk about space complexity. What if I have a function that has the name of Boo, and all it does is it takes an input, and within this input, it's going to simply have a loop that we've seen before. And this loop, let's make sure that I do this properly. Let's say that n.length, and we'll say I++. And this function is a really useless function that just simply logs out console.log Boo. Scary function. So now in here, if we just run the function and just give it an input of, let's say, 1, 2, 3, 4, 5, and run it, well, we have Boo running 5 times. And we know that the space complexity of this function, or time complexity of this function, is O(n). But when it comes to space complexity, let's think about this. What is the space complexity of this? Now, try to guess before I go into the topic. The one gotcha when it comes to space complexity is that when we talk about space complexity, we're talking about additional space. So we don't include space taken up by the inputs. So we don't really care how big the input is. I mean, we do care, but when it comes to this function, we don't really have a control over what sort of input it receives. We only have control of what happens inside of this function. So within this function, are we adding any space? Well, not really. The only thing we're really doing is we're creating this let I equals 0 variable. And that's it. Other than that, we're not really adding any more memory. So this function has a space complexity of O(1). Nice and simple. But what if we have a different function? What if we have something like this? This time we'll have a function that says array of, I'm going to give it another terrible name, high n times. God, that's a terrible name. But let's say that this function takes, again, an input. And within here, we're going to create a new variable. We're going to say let high array is going to equal an empty array. And within here, we're going to have a loop. I'm just going to copy this for now so I don't have to bore you with my typing. And in here, I'm going to simply say high array in the index. So as we're looping, we're going to fill it up with high. And we're going to return this array, high array. All we're doing is we're creating a new array. And for the number of items in our input, we're going to just fill up high array with repeatedly high string. So if I do this again and I say array of high n times, and I give it, let's say we'll give it, and you know what? Instead of length here, let's just leave it as a number. So I'm going to say n, and I'll say 6 times. So if I run this code, we see that even though we have the boo over here from the beginning, the other function, array of high n times, returns us a new array with 6 items, and each item just simply says hi. What is the space complexity of this? Well, this should give you a hint. Remember our cheat sheet. Variables, data structures, function calls, allocations, those things take space. And in our case, we created variables in our loop, variable I equals 0, but we've also created data structures, right? We created a new array. So now if we go back, we see that in here, we've created a new array and we fill this array with n loops. And again, because of our rules when it comes to big O, we ignore the constant time, let I equals 0 space, and instead this becomes O of n, because we're creating a new data structure and adding memory, so each item is an additional memory space on our computers n times. And you know what? That's pretty much it when it comes to space complexity. I think you're getting the idea, and we'll get a little bit more into it when we talk about recursion. But when it comes to space complexity, you're either adding additional memory that you need to use, and that's sometimes a big concern, and sometimes there isn't. And something that comes up a lot in interviews, and something that we'll talk about in the next section. That is, sometimes there's a trade-off between saving time and saving space. So you have to decide which one you're optimizing for. Let's get into some fun examples based on what we've just learned in the next video. See you in that one. Bye-bye. All right, let's do a fun exercise to show you that you've actually just become a better engineer. Let's have a situation. Let's say you're working at Twitter. And I hope everybody knows Twitter here. If you're working at Twitter and your boss asked you to build a feature, perhaps a feature that allows anybody to click a button next to their name and retrieve their most recent tweet and their oldest tweet. So that is their very first tweet and their very latest tweet. Based on Big O notation and what we know about Big O notation, what can we assume about this problem? Well, without coding anything, we know that we have to find first and then find nth, or whatever the last item is. Now, we don't know how the tweets are stored in our database or whichever way Twitter organizes these things. But based on how they are stored, we might be able to just grab, let's say the tweets were in an array. So let's say const array, and we'll have an array of tweets. And let's just say we have 3 tweets here. There you go. Just 3 simple tweets. We'll say that this one is the oldest and this one is the most recent. If we have an array here, we know that it's going to take us, if the tweets are stored in an array, it's going to take us, well, if we go array 0, we get the oldest tweet. And if we go array dot length -1, we get the 3 minus 1, so that is 2. So that is 0, 1, 2. This is going to be 2. We're going to get Teddy, the most recent tweet. And because of the way arrays work, we know that both of these operations will be O one time. And this one will also be O 1, or constant time. So a total of O2 operation, but we, again, use our rulebook and simplify it to constant time. So that's great. We build a nice little simple Twitter application and we can get that information very easily. But now our boss comes back to us and say, hey, I want you to compare the dates of tweets. So I want you to look at every tweet. Now within each array, there's an object. With each tweet, now we have, and this person does not tweet a lot, 3 tweets in 6 years, but now we have to compare each tweet with all the other tweets and compare their dates. What is the big O of this operation? Well, because we're comparing each item in the array with the other, this should sound familiar, we're doing nested loops. So this is going to take O and square time, at least with what we know right now. So we know that this is going to take a lot. And if it's a person that has a lot of tweets, a lot of inputs in the array, this operation might cost us a lot of money at Twitter. So you might want to tell your boss, we might have an issue here. We might need to do something else. Perhaps store this information in a better format or do something different with our program in order to avoid something that might be inefficient. It might be expensive for the company. And just by thinking like this now, you have this ability to think long-term, think scalable code. By the way, as a fun one, what happens if I ask you, what is the operation and what's going to cost us if I have a string and I do dot length here? In JavaScript, that just means what is the length of our string? That is 20. That means we have 20 items in the string. What do you think the big O notation of this is? And this is a bit of a trick question and something that you might get asked in an interview, because the answer to this is depends. It depends on the language that you're working with. We need to know how the method works on the string here, and that's built into JavaScript. And you'll have a different built-in method for your language. Based on how the language was built, this .length might go one by one and iterate over each letter and count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way until 20. But JavaScript actually has .length property built in to each string. So for JavaScript, this .length property is just a simple lookup. It's not a function. We're not running this function to calculate things. Instead, it's simply a property of an object. And because of that, and again, if you're not super familiar with JavaScript, this may be a little bit confusing, but don't stress out. The idea is that this operation in JavaScript is O, constant time. But without knowing how your language works, you don't know how this property might work. How perhaps if you had a method, how that might work. But now you have a powerful foundation, powerful pillar to start thinking about code in a different way. Start looking at space and time as something that are valuable to us as engineers, as resources that we must be careful. We don't have infinite amount of resources. We have to be careful when we code how we use up these resources. And that alone makes you a better engineer. I'll see you in the next video. Bye-bye. Big O says which function, algorithm, or code is best. We learned that when it comes to good code, we're concerned about readability and scalability. And Big O allows us to measure the idea of scalable code. And why do we care? It's because there is no such thing as a free lunch. You save time and money for a company, you're a superstar. Knowing how much time your code takes, how much memory it uses, is very, very critical. Those are expensive things for a company or a product. Now, Big O is a very important concept that you won't find in your day-to-day job, but it's something that should always be in the back of your mind. And good developers and engineers always have this knowledge. That is why it is such a popular topic during interviews. Big O is used to describe how efficient we can run our code. It saves companies a lot of money if people they hire know how to write efficient code. And in this section, we learned about the idea of time complexity and space complexity, how we can use Big O to measure both things, but each one is a trade-off between the other. And Big O describes the upper bound of our estimates. We're always looking at the worst case scenario. We want to be pessimistic and say, what is the worst case scenario here with our code so we can be prepared when the time comes? Now, time complexity and space complexity. Time is how long it takes the algorithm to run, and space is the memory that is required by the algorithm. The important thing that we learned here is that Big O is about how you can scale. It doesn't necessarily mean that O(n) is better than O(n) squared, because scalability wasn't the only factor, right? Readability is something that we were concerned with as well. Sometimes readability maybe matters more than scalability. Maybe time complexity is less important than space complexity. And that's something that you want to be careful of now with this newfound knowledge. Premature optimization can be the root of all evil. It's a famous quote that a lot of developers know. Sometimes optimizing for time or space can negatively impact the readability of code. So if you're working at a young startup, for example, it might be more important for you to write code that's easy to ship and perhaps easy to understand later. Perhaps not take as much time to write the code and think about the code and its implications for long term, because maybe the startup has limited budget and needs things done fast. That doesn't mean startups don't care about Big O analysis. A great engineer at a startup or at a big company knows how to strike the right balance between runtime, space, and of course, readability. The thing to keep in mind is that data needs to be sufficiently big to talk about Big O. It's about scaling. If your function is linear time, but the input is always, let's say, 7 items, then the linear time algorithm might be better than the constant time algorithm. So it really depends on your situation. I introduced Big O here because we're going to be using it throughout this course. And as we learn more about data structures and algorithms, we're going to learn more about Big O and some other things we saw in this graph that we haven't talked about. But I hope you now look at a code differently, and you had a few aha moments throughout this section. It's certainly my favorite section and a great topic that really made me a better engineer once I learned this topic. So I hope it did for you as well. At the end of this all, you have a way to look at code differently. And when someone says, hey, how good is my code? You have a nice new way of looking at things and measuring things. I'll see you in the next one. Bye-bye.